Alright, so the last two exercises that we did were kind of about getting up to speed for calculus, and now we're going to start working on the calculus part of the exam itself. So the big thing about calculus is really instantaneous rate of change. So let's review average rate of change and how it relates to instantaneous rate of change for a specific problem. And I think the most natural problem is just, Galileo's situation of a falling particle. So you can find this expression in the book. So S is traditionally used for location, or displacement. And the way a body falls, if you just drop it from, say, a tower, it falls at 4.9 times t squared meters. Right, so after t seconds, the body has fallen this many meters. So in the book, since the author of the textbook is like the richest man in Canada, the example that he uses is the Toronto CN Tower. So here's a tower. You imagine that you drop a ball off the tower, and the physics of it is, after t seconds, the ball has fallen this many meters. So for example, after, let's say, 2 seconds, the ball has fallen 4.9 times 4 meters, however far that is. So it's something like approximately 20 meters after 2 seconds. All right. So, the function that describes location is related to the function for velocity. First, let's talk about the average rate of change of this function. And so in this particular case, average rate of change just means average velocity. So let me draw sort of a picture of this. So it's really just a parabola. Whoa, okay. So even the computer can't stop me from bad handwriting. And, okay, so here, let's say we don't really care what happens when time is negative. You can imagine that when time is negative, the ball is sort of going up to the top of the tower. But let's just think about this part of the parabola here. So this is the graph y equals 4.9 times t squared. So in other words, it's just y equals s of t. This is the t-axis, this is the y-axis. And let's say that we want to know what is the average velocity of the ball between, let's say, the 3rd second and the 5th second. Okay, so here's 3 and here's 5. And I have a feeling I'm going to be doing some zooming in. Alright, so here's 3 and here's 5. Now, what average, just the definition of average rate of change is change in y over change in x. So it's just rise over run. So the average rate of change, or the average velocity in this case, between, maybe I can make my point a little finer here, between t equals 3 and t equals 5, it's just the slope of this line that connects these 2 points, the slope of the secant line. Okay, and so if I do everything out in algebraic terms, the average speed over this time interval is s of 5 minus s of 3 divided by 5 minus 3. Okay, and you will probably recognize this if you had a good pre-calculus class or you studied hard or something, as just a special case of the average rate of change formula. So the average rate of change of a function f on the interval from a to b is this. Okay, so this is the average rate of change of any function on the interval from a to b. So this is just a special case where the function is s and b is 5 and a is 3, and this is an actual number, right? So this is 4.9 times I'm not going to have enough space here, sorry. Just move this over. So this is 4.9 times 5 squared minus 4.9 times 3 squared, and this is all over 2. Okay, and now you might be thinking, I don't have a calculator. I am perfectly happy leaving it like this. Alright, so this is the answer. In third grade or in your last class or some other time, you might be worried about beating these things right down into a numerical answer, but I assume that you have some way of transforming this into a number. It's just arithmetic. I'm not really interested in that. So as far as I'm concerned, you can leave the answer like this. I guess it would be kind of nice to actually know what that was, though, just because this is a physical example, but I guess I'm a bad teacher because I'm not going to figure it out. So let's compare that to finding the instantaneous velocity at 3. Alright, so now let's work on a slightly different problem. So that's the average velocity over the interval between the 3rd second and the 5th second. So, but how fast is the thing falling at the instant 3? I'm spelling things wrong. Instantaneous velocity when t is equal to 3. Okay, so this is so embedded in our culture that I don't even need to argue that this really is a meaningful concept, right? Because we have speedometers in cars. At some point in history you could have challenged this idea, and I guess you still could if you're feeling philosophical, but I've never had a single student that found that interesting. It's a total fantasy of mine that somebody actually would, but maybe nobody just knows what the hell I'm talking about, which is really plausible possibility. So how do you do this? Well, let me go back up to my picture and let me change it a little bit. Well, I don't really want to change it too much because I want to put this PDF out for people to see. So maybe what I'll do is I'll make a copy of it. So I'm gonna, I hope this works, I'm gonna cut or copy and then try to paste a version of it down here. Alright, so now let me go in and kind of modify this so that it works for oh, I lost the t-axis, but that's okay, I can just draw that back. So there's the t-axis, and I didn't have my superpower turned on, so straight line hand. So yeah, okay, so that's not bad. And let me erase all this stuff. So now instead of thinking about the average velocity, we're going to think about the instantaneous velocity. Alright, so what's going to be happening now is instead of considering some point 5, I'm going to be just considering some point B. So what if we did that? And so what we're going to do is we're going to find the average velocity. Okay, so 2 steps here. One is find the average velocity on the interval from 3 to b, so b is standing in for some number now, and 2, that'll give us some expression, and then we're just going to let b go to 3. Right? So in the picture here, you can just kind of imagine that b is kind of in love with 3, and every time 3 looks the other way, b is going to scoot a little bit closer. And you know, this green line, the meaning of the green line is the average rate of change, the meaning of the slope of the green line is the average rate of change. And as b scoots over, the secant line, the line connecting these 2 points, is going to become more and more like the tangent line. And the tangent line is really, so the slope of the tangent line is exactly the instantaneous rate of change here. So the slope of the tangent line really is it's how we think of the instantaneous rate of change at the third second. So now let's implement our plan. So let's write down an expression for the average velocity on this interval. So first we can just use the abstract nonsense definition. So it's going to be s of b minus s of 3 over b minus 3. That's just the average rate of change formula. And so this is a real function. So this is 4.9 times b squared minus 4.9 times 3, and on the bottom here I've got b minus 3. Okay. And so that's it. So before b was 5, but now now b is just b, and we want to figure out what happens to this thing as b goes to 0. Okay, so this is kind of we're moving now from the end of the first step in our plan to the beginning of the second. Now we're going to look at the limit as b goes to 3. Alright, so first we should check and see if we can just plug in. And so if we plug in, we get 0 on the bottom. And actually we should get, you can see that we're going to get 0 on the top too. It's a little more clear from this picture, because here s of 3 minus s of 3 is just 0. So there's a factor of b minus 3 both on the top and the bottom. So let's see if we can get to it. Let's do it like this. Needs another page here. So there's a 4.9 involved that's not really doing much. So let me factor 4.9. I'm going to factor it all the way off to the side, and that leaves b squared minus 3 over b minus 3. Okay. And, oh, I forgot to square this 3, didn't I? Yes, sorry about that. So that 3 should be squared. Okay. And now you can probably see that this is on top, and the reason the 3 is squared is because of the formula. There's a square here that I ignored. See? Now, this is just the difference of squares formula. So on top I have, well, I'm just writing the 4.9 first. So I write b minus 3 times b plus 3, but my brain thought that I meant 6. So b plus 3. And on the bottom is b minus 3. Okay. And these things cancel out. The b minus 3's cancel. And what we have here is 4.9 times b plus 3. Okay. And now we just take the limit as b goes to 3, and this should be the answer. So we get 4.9 times 6. And so what is that? That's like approximately 30, right? It's approximately 30 meters per second. Okay. And all right, so this is the end of the problem. But let's use our, remember we have a secret way to evaluate the answer here. So, you know, the answer should also be by using our more advanced technology. The answer should be the derivative of y with respect to t evaluated at t equals 3. So using our differentiation rules, let's see if that is actually the same thing. So the 2 comes down and hits the 4.9, and that makes 9.8. And so now plug 3 in for t. So, all right. So this is also 4.9 times 2 times 3, right? Which is the same thing as 4.9 times 6, which is exactly what we got doing it the hard way, right? 4.9 times 6. So we got that one way, and we got it the other way too. So here's the answer, is 4.9 times 6. So great, that's the end of this problem.